Hello and welcome to this virtual storage developer conference. My name is Jerome Gaysse and I am Senior Technology and Market Analyst at Silinnov Consulting. I'm very happy to be here with you in order to talk about a very promising and exciting technology, computational storage. I'm sure you know very well the theory of operation, where the main concept is to move compute close to the data in order to reduce data movement, saving power consumption and increasing the system performances. The main goal of my presentation today will be to give you an overview on the different trends in terms of hardware and architecture technologies for computational storage devices. Then we will have a short overview on an hybrid system where we can integrate multiple technologies in the same system. And finally, how we can use it in edge and cloud environment. Let's start this presentation today with a few definitions as a reminder. The Computational Storage Technical Working Group at SNIA defined three devices: CSD, CSP, and CSA. The CSD is a computational storage drive, a kind of SSD with computing capabilities inside. The CSP is a computational storage processor, so a kind of accelerating card with no storage inside. And the CSA, which is at the system level with the integration of CSD, CSP, and traditional drives. Today I will mainly focus on CSD and CSP, since the CSA is just the integration of CSD and CSP. We can find a lot of different technologies, differences between CSD and CSP, especially on the computing capabilities. It can be based on a system on chip, or it can be based on a FPGA. Another difference between CSD and CSP or other drives is the way to use it and how we can integrate it in a system. Is it specialized with a specific function, or is it general purpose? And then we can more talk about a platform. This first technology description is a CSD with a system on chip for a specialized function. In terms of architecture, it is based on a custom system on chip, and this controller integrates both computing and function for storage and computing capabilities. On the storage side, that comes with NVMe and the non-flash channels, and FTL or error correction code as well. On the computing side, it is based on a multi-core architecture with optional hardware accelerator. A good example for this one is the Edge Fusion from NetInt. In this U.2 form factor CSD, you will have storage and computing. And what is specific is that you have specific hardware accelerator, I mean video transcoding IP for H.264 and H.265. So, for the user, the main benefit is that you can do this video application inside this device itself without using power-hungry GPU. So definitely this product is for a specific video application. This second type of technology is very similar to the previous one. It is a CSD with a system on chip, but here we are talking about a general purpose application. Regarding the architecture, so it is based on a system on chip with a multi-core architecture and including all the storage management which is needed for a storage drive. The difference will be on the computing accelerator. We will not find any very specific hardware accelerator, but only optional standard accelerator like compression or encryption. A good example is NGD System, a computational storage pioneer in this market, with the Newport platform. as it is specified in the name, it's a platform. Why it is a platform? Because NGD is providing the hardware and all the software environment in order to develop custom computational storage services. So what makes this product very good for general purpose? Because you can find it in multiple form factors. As you can see on the screen, there are ESFF, U.2, and even M.2 form factors. Another good point for making it very general purpose is that it is based on a Cortex-ARM multi-core architecture, and then the customers will benefit from the very wide ARM ecosystem. Now let's move to FPGA-based CSD, so very different compared to a system on chip, because the FPGA is programmed with RTL code. So it can be more complex, but the FPGA will provide better performance compared to a CPU core. There is no difficulties in integrating storage services in a FPGA, since we can find many NVMe drives on the market which are using a FPGA as a SSD controller. Like for SOC-based CSD, we can find specialized or general purpose devices which are using a FPGA. Here is an example of a specialized product with a ScaleFlex CS2000 available in add-in card or U.2 form factor. This product integrates a very powerful compression IP. It has demonstrated very good performance results for data analytics applications because it offloads the compression in this device. Even it is more complex to develop an application on a FPGA, we can still see general purpose FPGA-based CSD. Here is a very good example from Samsung. This is the Smart SSD product. This product is based on two controllers. The first one is a Xilinx FPGA, and this FPGA will handle all the computational storage services. For the storage part, it is managed by a Samsung SSD controller. Xilinx is more than a technology provider for this product, it's a real partner. Because Xilinx will provide to the Samsung customer everything to develop their own computational storage services. That integrates compilation tools, simulation, and the overall ecosystem of IPs. So we reviewed the different technologies for CSD. What about CSP? So as you know, there is no storage capacity in this kind of product, but it can be integrated very close to the storage, or even it can come with storage interfaces for an easier integration. Here, this is another example from NetInt. In fact, we can use their system on chip in different applications. So we saw them for the CSD with video application. By using the same system on chip, but without the storage, we can consider this product as a CSP. So the processing will be the same, but instead of processing the data, the file, which are stored in this drive, that will be on the fly for the NVMe interfaces by using the specific hardware accelerator for video transcoding, I mean H.264 and H.265. Let's see how we can design general-purpose FPGA-based CSP. For that, we will analyze the partnership between ADTCOM and Bitware. Bitware is a FPGA board provider. We can see more and more FPGA-based products in the data center world for intensive workload, such as HPC. But because there are new form factors for those cards like ESFF and U.2, we can integrate these boards in a storage system. So in order to design the full computational storage product, we will integrate IP from ADTCOM. ADTCOM provides IPs for computational storage in terms of storage services mainly. And a very interesting IP for ADTCOM is the peer-to-peer DMA. This IPs allows to connect directly a computational storage processor to an SSD without involving the host CPU. So, after reviewing the different technologies for CSD and CSP with specific use cases, let's think differently. I mean, why not using an hybrid system by combining CSD and CSP in the same box? Here is an example I have presented at the past Persistent Memory and Computational Storage Summit in April. If you want more details, do not hesitate to go to the SNIA website for the replay, which is online. The main goal was to evaluate the performance at the system level in terms of density, power consumption, and TCO. I have simulated different strategies. The workload was only on the server or on both CSP and CSD in this system, or with CSD only. Here in this slide, the example I'm showing is that I'm using CSD for encryption, compression, and database processing, and I am using the CSP for deduplication and erasure coding. The simulation results presented here show that the best results are obtained with the use of 25% of CSP and 75% of CSD, leading to a density decrease of 7%, a TCO reduction of 15%, and then power consumption reduction of 25%. For that, the workload is running at 60% on the host server and 40% on this hybrid system. It is relevant to think about this hybrid strategy because an application is running on multiple servers. So let's take the best computational storage technology for the right service. The drawback is that it adds complexity in the system design. Then, how to use computational storage technologies in the real world? The main targeted market and application for computational storage are the storage services with compression, encryption, erasure coding, and deduplication. Why storage services? Because this is the easiest way to integrate such system, because that will not modify at all the application. Another target is database, AI, and video application, as we saw with different examples. For AI, we are mainly talking about inference, since AI training is still recommended to be used by very huge GPU or specific chips. In an edge environment, a very integrated solution is appreciated, because we may have power and footprint constraints. For the footprint, I think that the CSD is the best device, because by definition, there is the storage and the computing integrated on the same device. Regarding the power consumption, system on chip will deliver better efficiency compared to FPGA. So we can use CSD with a SoC for the edge. For example, the M.2 is available with the Newport platform ASIC from NGD. Regarding the application, I think that at the edge we will have very application-specific computational storage services, like video or AI inference, but also some storage services like encryption or compression in order to reduce the data footprint and to protect it. I think that for cloud and data center environment, we can use all types of computational storage technologies, and even a hybrid is fine, as we demonstrated in the previous slide. In fact, the selection will be based on the use case and the application, of course, but also on the integrator profile. If you want to use a specialized CS device, it's quite easy. You just have to put in your system, it's like plug and play, and configure the different parameters, and that's it. If you want to use a general purpose CS device for your own computational storage services, then that will require very strong development skills. Then, as a conclusion, we can say that there are many technologies and architectures in order to design a computational storage device. It can be a CSP or a CSD, so with or without storage. It can be based on an FPGA or a system on chip, so very different in terms of programming model, power consumption, and mechanical footprint. And it can be specialized or a general purpose application. And for sure, we will find in the future other technology trends like interconnection between CPU and accelerators. There is not a bad or good strategy to use these technologies. In fact, that will really depend on the use case and the application. So, well analyze your needs, what are the constraints in your system design, and are you able to develop your own computational storage services? Thank you very much for watching this NIA presentation, and hope to see you in another conference. Goodbye!